It's my pleasure now to move us to the fourth presentation of the morning. And in this presentation, Professor Guy DeSouza from engineering is going to show us the mobile device that is being developed by our colleagues in engineering. Dr. Shu and Dr. Shu brought us together as far as an application for patients to be able to self-manage at home and report to their doctors and therapists, even monitor their progress themselves. We have seen a demonstration yesterday at our laboratory for that, and today you'll see like a video of some of the data collection that's done in that way. Dr. DeSouza has presented this work internationally at the International Lymphedema Framework meeting. This summer it will go there, and it went to the ISL this last session, and he's received some awards for this in the informatics world as far as the development of this tool. So we're very fortunate that he has become interested in lymphedema and is willing to partner with us in this way. I'll go in and do a little bit of housekeeping while we get that set. And okay. Oh, is it ready?
See? Oh, maybe. All right. I'm Latino, so I'm not supposed to be behind something. I have to move around and shake my hands and move around. I'm Guy. I'm here to present a little bit of what the research we are doing. Some demonstrations were done yesterday, so some of you have seen this, but we're going to see it in a more organized, formal way. My name is the only name here. By no means I am the only one behind this. Actually, Guanan Lu, sitting right there, is the man behind this, and of course, Dr. Armour and Dr. Shiu also great contributions in this work. So anyways, so I'm going to talk about mobile assessment of lymphedema. First thing is, and I have to apologize also for the code. It got worse actually from yesterday. But anyways, so the first thing is what is a vision guide, robotics guide doing here, right? How I got here. I answered this question yesterday, but today I want to blame the person. It's right there. No, actually, Dr. Shiu. He was the one to blame for it. So he introduced me to Dr. Jane Armour. And anyway, so that was 2 years ago. I was looking yesterday, almost 2 years ago. And so that's the quick answer to the question. It's his fault. So anything you don't like here is all his fault. The second answer is I've been, as a lab, we have been trying to get away from the things we were doing in the past and trying to get more involved in assistive technology, how to help people with severe disabilities. We use robots to guide wheelchairs, interface with computers, and things like that. So anyways, so that's one reason. The other reason, and and basically, sorry, I lost track a little bit here. Yeah, so I was talking about how we got involved into this. So we're trying to get away from, and trying to get involved with lymphedema. It actually is a great area. It's amazing. I was talking to Guanan earlier today, how you guys are so nice. Engineers are nasty people. We are not that nice, believe me. Conferences are, people, I was in a conference once that in Switzerland, they had this long horn, Swiss horn. When the time was up, the guy would blow that thing and you have to get out, So it's really, amazing. And not just this, it's really amazing to be doing something that can help people, that can, improve quality of life and improve, the health delivery and all that. So anyway, so that was the second reason. And the third reason is because, the more technical reason, is because robotics and actual vision connected to robotics is basically how to represent the world so the robots can interact with this world, okay? So we do a lot of 3D modeling. We do 3D modeling of plants. So we do field phenotyping. So we send robots to understand how the plants grow, try to improve, crops. We do phenotyping, we do robotics again for helping people with disability. So it was just natural that computer vision and robotic vision could be used to, help lymphedema. So We're going to make a brief introduction here about why we're doing this, the importance of this. Of course, all of you know the importance of doing this, but in our point of view, what we are targeting here is self-monitoring. And I used this term yesterday, and then I showed the system, and a lot of people said, oh, that's not self-monitoring, because you need the husband, you need, right, a spouse to help, right, collect the data. And that's right, but this is a research. We're still, moving towards this. Hopefully, we're going to help get to the self-monitoring of lymphedema. Technically, I'm going to talk a little bit so we don't get too bored, but technically what we did was we developed this cost-to-fine registration approach. That's the technical term for what we do in terms of 3D modeling and how to combine the 3D data. So I'm going to talk about a little bit of this. Again, our goal is to develop a system, an imaging sensor that can be used for self-management, that is user-friendly, that's reliable, and can eliminate some of the burdens that patients in lymphedema have to go through. All right, the background is even more known to you, even more. I just want to point out basically statistics that I know they're conflicting. Some people talk about, Dr. Roxon was talking today about 1 in 5 patients. But I think some of the conflicting, statistics is sometimes things like that, 2 years after surgery. So it's a very specific group, the group only with surgery. But again, my point is a lot of people will develop lymphedema, and a system that can help people not self-diagnose, but help people to monitor and quickly, early diagnose of lymphedema is definitely something we have to to aim. The other thing I want to emphasize here that relates to what we are proposing is again a system that eliminates the burden from patients that already going through treatment have to go to the clinic to do the measurement, and it's an additional burden that we are trying to eliminate. That's our goal. All right. So the systems that those patients usually rely on, the physicians and the nursing professionals, they rely on are the water displacement, the circumference, the impedance, pedometer, the DEXA scan, and on the very end is ours. So we did this comparison between all the systems, and basically we were targeting this kind of behavior alpha system. So basically we want a system that was low in cost, very low in cost. It didn't require any time to operate. And this is an interesting thing. When we set up this table initially, we set up this table for the water displacement as moderate. Soon enough, I changed that because we did some experimentations, and it's a pain. It's very careful. You have to stand for a while until the water stops dripping. It's painful. It's really painful. And and I bothered, Jane a lot, calling, hey, are we doing the right thing? Are we measuring this way? Are we, supposed to do this? And anyway, so I went to the table and I said, you know what? Not moderate. It's high. It's really high time to operate. But again, we want something that was low time to operate, inter-rater disparity. That was something we definitely wanted. We want a system that you can hold, you're going to see a video or some image, but we can hold, you can grab your arm, and, absolute automatic, no error due to, the way the rater holds the device. What else? Maintenance. Again, maintenance. Some of these systems are really high maintenance. The other thing we're targeting that's very important to mention, I'm going to show some results. Local measurements, right? A lot of those systems cannot identify very small swelling, right, in hands or arm. So again, we are targeting something that could perform local measurement. Yes?
Can you say why you consider the parameter high pre and post maintenance? What do you mean by pre and post maintenance? What is that category?
The maintenance, we are talking about disposable material that you need. For example, in the case of the impedance, right? You have probes, you have things that needs to be, right?
So that would be considered high maintenance.
Yes.
What do you consider high
And
maintenance?
also,
Oh, go ahead.
okay, no, go ahead.
What do you consider high maintenance about parametry?
The parametry, the high maintenance was, I think, just the cost of replacing parts and, right?
There's pretty low maintenance on them
So,
over time.
yes, it may be, it may be,
That's easy. That's easy.
all right, so it's, we should change that. All right, thank you.
Thank you.
Again, these are the two gold standard. If you, actually the water dispenser might be, the gold standard, but the pedometer, you guys very familiar with this. And this is our, proposed system. That's the first generation of our system, the one we demonstrated yesterday. We have more results from this system. It basically consists of a Kinect device, a video game device that most of you have at home or your kids have at home, with a small gyro. I'm going to talk a little bit more about that. But again, the idea was for the person to, raise the arms, and then, with the device you could imaging and create 3D models of the limb. So this is actually part of a much bigger system. Somebody asked yesterday also, this is a much bigger part of the system. The whole idea is that you may have your Kinect or your iPhone. The second generation of this system is using smartphones. But again, you have your equipment at home, you collect the data, and you upload that information to a server where that information is cataloged, is part of the database that Dr. Shi was talking about earlier. So this is just a small component of this, right? So I'm talking about how this component interacts with all the the data collection that Dr. Shi was talking about earlier. Yes.
Okay. The older generation is not up to a lot of the data that you're presenting up there to keep track on, like a computer or whatever, an iPhone and stuff like that. A lot of people do not have that knowledge. So how are you going to connect, how are you going to collect your data?
A lot of people don't have knowledge of the device.
Right, they don't have the knowledge of the
Yes.
iPhone or the computer to be able to go in and do this with.
Yeah. Okay. The Kinect system, right? All the person has to do is to hold and move around, right? Would be the click of a button. There was some questions yesterday exactly about that, because yesterday we didn't have time to do the full presentation. So what we did actually was Guanan went to the computer and started trying to find old images, and it sounded like it was a very complicated process, but it's not. The idea is you click a button, you go around with your Kinect, and uploads to the server and does the volume calculation and returns the result. The result can go directly to your physician, right? Or could go to your phone or to email, right? It could be sent to you the volume. You don't have to understand how it's done.
Okay.
All right. So again, just to give you an idea, I'm an engineer, so I'm trying to brag, right, and say that this is very hard, this is very hard work. What the problem here is basically, we hold this device, right, around, the person, and we move around the person, and this device is collecting 3D points. Okay, so it creates this, what we call a cloud of points. So you have this, right, cloud of 3D points, and every image that you hold is basically one cloud of points. Okay, so again, the guy doesn't need to know that, right? He's holding the device, right? And every time he moves the device is collecting clouds of points. Okay, and these clouds of points have to be registered, right? Some people call registration, some people call stitching. You stitch the clouds of points together to create one single 3D model of the arm. So that's the difficulty of the system, and that's what, yes?
For those of us that would like To know, can you walk us through your equation, please?
Walk through the equations? Yeah.
Right.
Good. I like that. All right. What this equation here represents is basically every position of the sensor has a coordinate to space. And the system requires the position, the relative position between two consecutive images to be determined. Okay? So these matrices here, they represent the transformation of one coordinate system to the next. I love that.
So basically, so your n in your equation is for each point, right? In your equation?
Yes.
And then the r is equal to what?
Yeah, the R is the one that's there. It goes from 0
Your reference.
all the way to n minus 1 for all the n positions of the system, the coordinate system. Okay? I'm probably making the guy back there crazy with the camera. Follow me. Right? Yeah, it's going to make him the money he's getting for it. Right? All right. The system consists of all these steps here. So it's basically you collect the raw image. We go through what I was talking about, this coarse to fine registration. Every, probably 90%, 95% of any algorithm in computer vision or engineering mostly, and maybe I'm too, anyways, but they are optimization algorithms, okay? And without the proper initialization, the algorithm doesn't work, okay? So what this guy here does, the coarse registration, initialize the process for the fine registration. Okay, that's what it does. The fine registration is the algorithm that we developed. I'm going to talk a little bit about it. Then we do integration. Integration is basically throwing away everything that's not required, that's redundant. And finally, we do smoothing and surface reconstruction. I think I'm going a little faster here. That's okay?
We'll let you go to at least 5 after we run questions as we go into lunch.
All right.
So there's
So I have to go real fast. All right. So let me go to the bottom line maybe. So again, the coarse registration is this algorithm that, again, we developed, is based on an IMU. IMU is an inertial unit, a movement unit, and it's basically something, again, it's Algorand's fault in this case. It's basically an algorithm, a system that allows you to measure the acceleration of the device. Every cell phone has this, okay? Your cell phone, when you point, to a certain direction, it knows that because it has a magnetic, compass, but also because it has gyros and things like that, okay? Accelerometers. So again, that's a perfect device, for us to base our system. Right now, we are using the Kinect, so we had to install a little device on top of the Kinect to perform the same, function. And for you, it basically helps us to initialize those matrices, okay? Those coordinate frame, matrices. So again, just quickly, just to give an idea, this is what the coarse control does, the coarse registration does. So these are two clouds of points, okay, obtained from two different, positions of the sensor. After the coarse, you see that they are almost aligned, okay? And once they are almost aligned, then we can run our fine integration, which is basically an algorithm that minimizes, again, it's always minimization, minimize those transformations and try to find the set of transformations that move one cloud point on top of the other one, okay? The algorithm we developed is what we call the ICCP, Interactive Clustered Closest Points, which is basically an algorithm that clusters the cloud points and then classify them based on the distance they are. So if you have, for example, one image like this, right? This part here is further away than this part here. So we try to move this part, quicker, right? By assigning different weights for different parts of the limb. All right, so this is the result, okay? So now you see the same two, views, okay? Not on top of each other anymore, but the same two views, and these are the combined view. So you see that you see some red points and some blue points. That means they are so close that sometimes the blue points are displayed, sometimes the red points are displayed. Okay, so that means that is a good, registration. All right, we do a lot of processing after that. So let me show you again the results. So you guys probably saw yesterday we had, what is she? April? Yeah, what is she? She would like to see her. Okay. So we did yesterday, we collect the data from April, and this is the result. But this is the raw data, okay? That's just the raw data before any processing. This is after some processing. You start to see her, face. You can see even her badge, right? And then the final model is this one. So that's April 3D modeled. Yeah. Yes.
Determine a good image or not.
Oh, okay. Actually, it's not just the red and blue, right? We have,
multiple
how many we have,
views.
Guanan? 30? How many views we have?
30, yeah.
About 30 views. So we collect 30 views. So we're trying to stitch all 30 views together.
But how much agreement are you looking for across those views to make sure that you've got a good image before you go into your smoothing and filtering?
You mean the condition to terminate the it's based on the error, right? We try to get error as close as millimeters, or right, 1 millimeter. So it's a combination actually. It's a combination of the error and the number of iterations. Sometimes you iterate, it doesn't converge, you have to stop, because that's the max we can get in terms of accuracy. Again, just to emphasize again, this is totally automatic. Okay, even the selection of the 30 images is automatic. All the person has to do is to, move the sensor around. He actually collects 30 frames per second, so he collects a lot more data than that. The algorithm selects 30 of those, the best 30, and then creates the model out of those 30. So it's all done automatically. All right, so we did some experiments, and that's probably the part that you're more interested into. So how do we know this works? How do we know that is measuring the volume? How do we compare this to the pedometer or the water displacement? So we did 3 experiments that I'm going to describe here. One with the pedometer, one for the accuracy of local measurements, and the third one with the water displacement. So the first one, again, with the pedometer, we compared I'm going to show 3 out of 12 that we did. The first one is a typical one. The discrepancy between a typical arm, the volume measured by the pedometer, the volume measured by our technique is about 5%. So these are, so this is one of them. The worst case was a lot bigger. We wonder if it's because, again, it's so hard sometimes for especially for me, I'm not a nurse. It was difficult sometimes to remember from one day to the next. Well, sorry, this is not the justification for this one, but again, since I'm saying for the water displacement, right? It was so hard for us sometimes to know the exact position that the arm went into the water. And any centimeter that you have, that's a lot in volume, right? So we didn't know if we were collecting the same length of the arm. Okay, which was the case here also. We don't know if it was, when we did, the 3D image, we were cutting in the same exact spot that the pedometer was, cutting. So it's not that our technique is wrong, is that, it's hard to compare the two when you don't have a common reference for both techniques, and you mark, the arm at the same exact position, both techniques. The third case is a case of a person with lymphedema, and then again, that was a very good result, about 9% discrepancy. I'm going to speed up here. The second experiment, like I said, was can we detect a small, very small, localized swelling. So we did a measurement. We put a pen, okay? We taped a pen on the person's arm, Guanan's arm. So we measured, before and after, and the difference between the two volumes was exactly the pen, right? The pen was measured to have 9.5 milliliters. The estimated, we don't know the exact volume of the pen, but we estimate to be 11. So again, it was able to detect, and then what was more important, that the pen represents only 0.5% of the total volume. So we can, detect a change in volume of 0.5% of the arm, the total volume. Pretty bad, measuring the water displacement. Sometimes we got 7%, but you see the difference between our technique, right? Sometimes it's very, high compared to the water displacement. Again, we don't know if it's because of the volume, if it's because of the weight, right? The length of the arm that we used. So anyways, so again, this is our current future work. We are using now cell phones. We are looking for volunteers. We are running an IRB to do, and I have some flyers here. If you want to contact us, and all right. So if you pass around. The IRB is not approved yet, so I made a very large disclaimer that it's not approved yet, but we are trying to get approved. The idea is to use the cell phone. The only difference here is that because we're using cell phone and not the Kinect device, the person has to wear a sleeve. And it's basically one of those, it's a $1.50 sleeve that we bought from the web for people who wants to fake tattoos, right? So they wear those. So they're not compression garments or anything like that. This is the result we got so far. This is the 3D model. Again, you can see the the arm in 3D. And I think I'm done.
I will say in just a moment, we'll let you go to get your lunches, and maybe Guy would be kind to stand here with us and take more questions. We've been recording until right now, and I saw on the screen, I think the recording thought we stopped at 12, and we'll start again. So I asked Nathan to try to keep them recording.
Nobody likes engineers.
So you may